Okay, I'm going to go through part 2. This recording, I just uploaded part 1, so it'll be with you shortly. So this is the Pearson Edexcel International A-Level Physics exam from January 2025. It's the most recent in the series for the International A-Level, and it also doubles up as good practice questions for the students doing the linear version. Okay, so if you're doing the linear version, I recommend you doing these papers. So the International A-Level has 3 series a year: January, June, and October, whereas linear only have sittings in June. So your linear exam is coming up in June. That's meant to say June. So the linear exam is coming up in June, is slightly later because in the linear exam, as well as knowing all the content for the Unit 5 content of the International A-Level, you also need to know the Year 12 content. Yeah? So the linear exam includes all these topics, exactly the same specification, plus Year 12. Yeah? Content for the topics that you need to think about. So for example, because of cosmology, they include questions on optics, and they include questions on spectra. Okay, so spectra, you were taught spectra in Year 12. So what I'm going to do in this run through, so although it's primarily for students doing the International A-Level, I'm going to put the questions in the structured section together as topics. So you can see I'll do thermodynamics, and then I'll do questions on oscillations together, and so on. Hope that will be helpful to you, and I'll also share them in the linear playlists. Okay, so let's go straight through it. In the first section, I did the multiple choice already, so it'll be in the same playlist for Unit 5, and probably in the same playlist if you're doing linear as well. Okay, so I teach both, and the content and the syllabus, even the chapters in the textbooks, are more or less identical. There is optics in linear, which is not included in the International Unit 2 section of the Year 12. So I went through the multiple choice questions, and I didn't show you the mark scheme. So this is the mark scheme way that they give you the information. The other good thing about the International, I think their mark schemes are a bit clearer than the linear, so they're really good for practicing. Okay, but the main thing is there's more papers for you to practice, and it really helps you to fine-tune your knowledge of the Year 13 content, and you can likewise use the equivalent units from the International run-throughs that I've got on my channel to fine-tune your knowledge of the Year 12 content. So for example, Unit 5, the content they give you is on thermodynamics, nuclear energy, oscillations, and this is, I put this at the beginning of the paper, so we actually look at it: simple harmonic oscillators, astrophysics and cosmology. So this is exactly the same as the linear. So you see I've used V equals H naught in the multiple choice question 7. And remember, they don't give you this equation, so you need to remember that equation, that the age of the universe can be worked out from the Hubble constant by making the reciprocal. The other equation we use in multiple choice question 6 was making use of the mean kinetic energy being equal to the temperature in Kelvin, or directly proportional to the temperature in Kelvin if you use Boltzmann constant. So it's really useful becoming familiar with all the equations you need to know, okay, or be able to use. And section B is very similar in both the linear and the International A-Level. So here they give you a mass of a spring, okay, it's displaced. So the equation for a spring mass system is T equals 2 pi root m over k. The mass is displaced vertically, so obviously you're going to set it into up and down vibrations. Okay, so it's going to go down, up, vibrations. Okay, so the mass oscillates vertically with simple harmonic motion. So this is about simple harmonic motion, and the defining equation for simple harmonic motion is A equals minus omega squared x. Okay, so, and they're giving you the period relating to the 0.35. Then extra mass is added, and the period changes in the second attempt using this equation. You've got to work out the extra mass. Okay, so how do you do this question? So this is the method. Use the values given to find k. Yeah, so obviously in the first one you can use the values given here to find k. Then you can use the value of k that is constant, the spring hasn't changed, and then you can work out m in here in part 2. Then to work out the added mass, you've got to subtract m2 from m1, and the mark scheme uses this method. However, so I'll show you the mark scheme in a minute. However, came up with the algebraic solution, which the mark scheme refers to. So because I changed the equation t equals 2 pi root m over k by squaring both sides, there's another way of doing it. Ignore this, that's just my mistake. Okay, so once that you do that, you know that t squared is proportional to m. Therefore, you can just do a ratios method, because t2 squared to t1 squared must be proportional to m2 over m1. And therefore, we can work out, because we know t2, we know t1, we know everything on this side of the equation when you make m2 the subject. And I just put the numbers in, and I came up with the same answer as the examiner. I just think mine is a very neat method. It allows you to realize that if this is a multiple choice question, this would be the method I would recommend. And then you do the change in the mass from m2 to m1 to get the final answer. So this is an alternative method they would accept. The mark scheme refers to it, but doesn't show you this one. Okay. The worst mark schemes, by the way, that I've seen are AQA. So that immediately, as a teacher, would put me off using AQA as an exam. Okay, so if AQA people are listening, I doubt whether they will, but I think AQA have got it wrong. Their mark schemes are very confusing, even for a teacher. They don't show you this kind of solution that they want students to be able to use. So this is the first method, yeah, and they say allow use of the equations to work out the ratio of the periods, which is what I did. Okay, so as long as you've used t equals 2 pi root m over k, so I did. Original mass subtracted from the new mass, I did, and get the final answer. So they don't mind which method you used for question 11. Hope that makes sense. I just thought it was useful that you can see there's two methods of doing this question. So my run-throughs are not to write down the model answers for you. That's your job. My job is to explain the underlying way of reading the question and making sure that you don't make poor communication choices, and even things like your handwriting will make a difference. The examiner will be tired. They're doing this on top of their normal job. They will be tired at the end of the day. If they can't read your writing, you're going to lose those marks. Okay, so that's for some of my students who they know who they are. The graph shows how the gravitational potential varies with distance, okay? From the center of the Earth, you'll notice that all the values of potential are negative, yeah, because the equation comes from V equals minus gm over r. So in other words, potential is always negative gravitationally. That shows, negative shows that gravity is attractive, because things always move to minimize their energy. So imagine we're going the other way. So imagine we're going this distance away from the center in the positive direction. Do you agree that you could also go this way away from the gravitational attractor. In this case, it's for the Earth. So do you agree that the closer you get, the stronger the gravitational field will be? So if you imagine it, you would have a reverse curve. If you had the negative side, you'd also have a reverse curve there. And I like to explain to my students that basically the Earth is a gravitational well. So things kind of fall into the well. I hope that helps you with the concept of gravitational potential. And the only place where gravitational potential is zero is if you actually go to infinity, go where r, the denominator, will be very, very large. So v will become zero. So that's the only place where gravity doesn't have a value. Everywhere else is negative because zero is greater than negative. Okay, so hope that helps you. And they're going to ask you to show that. Yeah, so show that means prove mathematically that the mass of the Earth is about 6 times 10 to the 24 kilograms. So we don't use this value. We've got to show that when you put the equation round this way, yeah, you can use it by putting the numbers in, using the values, taking two corresponding points from the graph. Now the examiner has taken these 2 points. Okay, they put those 2 points in. So I thought I'd take 2 different points. So you got 2 answers that come to the same value. So I've taken 0.05 in the negative potential and 0.8 there. Yes, times 10 to the 8, don't forget. And the other one's 10 to the 7. So 0.5 times 10 to the 7 multiplied by 0.8 times 10 to the 8 divided by the universal gravitational constant. Whether you use the examiner's values or mine, it should give you the same response. And you should then round it up to one significant figure to prove that you have shown that. Okay, so show that means prove it mathematically. Okay, note obviously we don't have a negative mass, so you don't need to worry about that. That's just to understand the potential is always negative. Okay, so here is the value used by the examiner. Okay, so that's 2 questions on gravity really, because a spring mass system also is in a gravitational field. So it's kind of similar. So I'm going to do 11 and 12 in the same paper, and I'm going to go and look through this. This one is using heat. So I'm not going to do the heat questions right now. I'm doing anything to do with oscillations or gravity. I might not be able to do them all in one go, but I'm going to try. Okay, question 14. This time gravity, Earth takes 365 days to complete an orbit of the Sun, and that's 365 days. At first I thought they'd given us 1 day. They've given us 1 year in seconds. So you can just change that to 3.15 times 10 to the 7 to put it in SI units in seconds. Okay, they want you to again show that the mass of the Sun is about 2 times 10 to the 30 kilograms, and they've given us how far away the Earth orbits the Sun, 149 million kilometers. And obviously from the time period, we already know we can change that into angular velocity by using 2 pi over omega. Okay, now obviously this is a circular motion question, so it's revising circular motion, and that's why you do further mechanics before you do gravity. And if you change, you can see the mass of the Earth is not needed. You just need to know the period and the distance. So if you change the subject to make mass what you want to do, because you want to show that the mass is equal to 10 to the 30 roughly. So you put in, you'll notice it becomes r cubed omega squared over g. So you put the omega in here. You put the r value in there, cube it, square it, divided by g, you'll get the mass. Okay? You have then shown that the mass is about to one significant, you need to then, you need to put this is approximately equal to 2 times 10 to the 30 kilograms to one significant figure. So they say about means to one significant figure because that's what they're giving you. But we put 3 significant figures here. It's good to show you do 3 significant figures and then show that you're going to put it to the value that the examiner wants you to be able to show that it's approximately that. Okay. Part B, it says television program claimed that the gravitational field strength of the surface of the sun is 28 times greater than the gravity of the Earth. Well, the gravitational field strength is dividing the force, Newton's law of gravitation, by the mass of the smaller object. Yes. So you don't need to have the mass of the object, so it'd be per kilogram if you like. Okay, so obviously at the surface it tells you how many newtons per kilogram the gravitational field is. So we know at the surface we need to use the diameter, the radius of the sun. They've given us the diameter. You've got to work it out the radius to put it into this equation, and you just put the numbers in and you'll see that it's 270, approximately 271 newtons per kilogram, and this is Earth is 9.81, so you divide the ratio and you get 27.6. So yes, what are they asking for? 28 times. They're asking for show that it's 28 times. Okay, so it's another show that, except they say deduce. So we have deduced it. Okay, so claim is correct. So again, you see, I do accurately to 3 significant figures, and then in this case, rounding up to 2 significant figures because they want to show that it's approximately 28 times. They could have said show that it's approximately 30 times, and obviously to 1 significant figures, it's approximately 30. And there's another 6 marks done. Okay, so we've done some gravity. Let's look at see if there's any more gravitational questions. This is again the helpful way that they've done it. They've made a mistake by multiplying the 365 when they didn't need to, because this is 365. So there's just some confusion in the typing. You can see that they haven't put it in here. Yes, they just, in the first sentence, they did that. It really confused me at first because I was wondering how did they get that with 365 at the bottom? Then I realized that they'd made a mistake. Okay, so even examiners or whoever types up the examiner's notes can make a mistake. Okay. And it's normal to, even under exam pressure, it's normal for students to make mistakes. So question 14 done, 6 more marks in the gravitational field section. This one is resonance, so it's more to do with simple harmonic motion. I could do this because we did the vibrating spring question, but this is a little bit more detailed, so I'm going to come back and do this in a separate run through. Yeah, here we have standard candles, so it's to do with luminosity, so we're going to do that in a separate question. And so this is a quick run looking at the questions. Here we've got simple harmonic motion, so I'm going to do this 2 simple harmonic motions together and the oscillations. Okay, so let's see what's left. Here we have spectra, so this is useful for this is also revises unit 2 of IAL and very useful for linear students. Okay. By the way, if you know any students doing linear, please let them know that I'm starting to do linear exams. If you think my videos are helpful, let them know so we get a greater following in the linear world as well as the A-level modular world. Okay. Heat, pressure, so we're going to do that separately. 19. What else is left? 20. So that's all the gravity questions done. Okay. So I'm going to come through and do the rest of them. I think this is the last question in the paper. Oh no, there's another one. This is radioactivity. Okay. All right, so we'll come back. 21 is the last question, and uses E equals mc squared. So that's the full 90 marks. So you can see that both the linear and the international A-level have a 90 mark, 1 hour 45 minute paper. So if you found it useful, don't forget, show your appreciation, like and share. I told GCSE students I'm not making as many GCSE papers because I get more interaction from A-level students The A-level students are liking the videos. I get more likes, I get more shares, I get more interaction with A-level students, and the GCSE students watch them. For example, there's 270 views on the one I did recently last month, and only 3 likes. So if you know GCSE students, can you educate them into the etiquette of YouTube? Because that's basically, YouTube people will not make videos unless they get positive feedback. Okay, that's it for now. Catch you in the next video. Thank you.